Hello, Chem 1B. This is Chapter 14, Lecture Video 4. And in the last lecture video, we talked about rate laws. We're going to start with a rate law problem here. If you haven't watched that video, you should watch that one before watching this one, of course. So we learned last time that the rate law is really dependent on all the rates of our reactants. So let's look at a problem. So we have a reaction that is A reacts with B, goes to products. And we don't really care about what the products are because we're talking about a rate law, and rate laws only depend on the reactants. And we're told that the reaction is third order in A and second order in B. Now, we can build a rate law just from that statement. We know that the rate law is going to be rate is equal to K times the concentration of A, our reactant, times the concentration of B. And because we were told it's third order in A, that's really like saying, hey, the exponent of A is 3. Or that it's second order in B, that's the same thing as saying, hey, it's squared for B's concentration. Now, this is our generic rate law for this A-B reaction. Now, we're told now that the concentration of A is doubled and the concentration of B is tripled. And we want to know by what factor would the rate of the reaction change if that was the case. Well, so there's the theoretical way to solve this, and there's the quick and easy way to solve this. So we're going to do both. So what I would do first is I would say, hey, let's say these are our initial concentrations, which are usually designated by a little 0 there, like a naught, but I can do i's instead. So we know that these are initial concentrations and they're squared, right? Or in cubed, depending on which one we have. Well, let's say, hey, we know rate K times A final times, B final is still squared and cubed. Well, we know how the initial and the final differ from each other, right? We know A concentration final is equal to 2 times the concentration of A initial. And we also know that the rate, or the concentration, sorry, of B final is equal to 3 times the concentration of B initial. Now, I can plug these in here. Oops, sorry. Plug those in there into our equation here, right? Just take both of these and plug them in. And then I can use the relationship between these two to kind of solve this theoretically. Now, how do we do that? Well, let's go ahead and try. So I'm going to put rate final here is equal to K times the concentration, times quantity, 2 times A initial, and that whole thing is cubed, times 3 times B initial, and that whole thing is squared. Now, I don't know what A initial was. It didn't give me that in the problem. I just know I tripled it and doubled it as far as the concentrations in the reaction. Well, if I divide this by rate initial, and really that's what we want. We want this because we want to know what factor the rate changed by, and that's really just the rate final divided by the rate initial. That's just going to be equal to K and all that. So if we divide these two rate laws, really this is my initial and this is my final, then I can get this. Now, we notice the K's, they didn't change, so they just cancel out. These exponents, they distribute in. Which means I have B initial squared here, that cancels, and A initial cubed, that cancels. And what I'm left with is that rate final divided by rate initial is equal to 2 cubed times 3 squared. I can solve for this value. And basically my factor that this changed by is 72. Right? And so that's my answer here to this type of problem. Now the quick and easy way would have just been, hey, just plug 2 and 3 into your original rate law respectively, ignore k, and cube and square them, and you'll always get the same answer, right? So like for instance, if I had said instead, hey, A is tripled, B is doubled, switched it, right? Then my rate of change, or the factor of change that the rate changed by, right, it would just be A's tripled, A to the power of 3 times B to the power of 2, if I doubled B, right, if I change this problem. And then that's the whole thing. Or in this case, right, I could have just gone, well, it's just, you know, A is doubled, so A squared, or 2 cubed, sorry, and B is tripled, so 3 squared. And done. That's the whole problem. That's like kind of the quick and easy method. This is the whole theoretical mumbo jumbo. If you want to use that, by all means, you don't have to, though. You could have just plugged straight in and solved that way on a test or a quiz, and I wouldn't have minded. Okay, so let's talk about how to actually experimentally determine a rate law. So let's say we have this data here given to us in a problem, and we want to determine the rate of this equation here, or the rate law, sorry, of this equation. We have a bunch of initial rates here, and we have concentrations that for both of our reactants given in this table, and we did 3 experiments. So let's talk about how to determine the rate law in this scenario. So here's that data table. I copied it straight. Now, if I want to do this, what I need to do is I need to realize that in this equation, my rate law is going to be K times the concentration of NO times the concentration of H2. These are my reactants, and they are to some exponential powers that we do not know. I'm just going to use X and Y. I cannot say that both of them are 2 just simply because, you know, they were 2 up here in the equation. Remember, these exponents are not based on stoichiometry for overall reactions. So how do I figure this out? Well, I know that K is going to be the same regardless of what concentration these guys are at. But I do notice that, hey, here in these 2 rows, the concentration of NO stayed the same. So I need to find a way to eliminate one of my unknown variables. Right now I have 3. I have K, I have Y, and I have X. I have no idea what those values are. So let's look at how we can eliminate 2 of the 3 to get at one of the unknowns. If I use these 2 rows, I can say, hey, rate 1, we'll say rate 2 over rate 1 has to be equal to K over K times the NO concentration, 2 to the power of Y, times H2 concentration, rho 2 to the power of X. And down here it'd have to be NO 1 to the power of Y and H2 1 to the power of X. Well, if we plug some values in here, right, we have the rates, we have the concentrations, let's see what happens, right? So I have 2.46 times 10 to the negative 3 divided by 1.23 times 10 to the negative 3 is equal to K over K times the concentration of NO, which is 0.10 molar to the power of Y, over 0.10 to the power of Y, times 0.20 to the power of X, over 0.10 to the power of X. Now, if you notice, K is going to be the same, so that cancels. And whatever 0.1 is to the power of Y divided by 0.1 to the same power of Y, these 2 are going to cancel. So effectively what I get, if I take this kind of over here, right, I'm going to get 2, because if we divide these 2 values here, you get 2, exactly, is equal to 0.2 to the power of X over 0.1 to the power of X. Now, since we're taking them the same exponent, we can actually factor this out and say, hey, 2 is equal to 0.2 divided by 0.1 all to the power of X. Now, at the end of the day, this means 2 is equal to 2 to the power of X. X can only be one value if they're equal numbers. This tells me that X has to be equal to 1. Now we can do this all over again with two different rows of experimental data to calculate the exponent of H2, or sorry, NO, because we have H2s. We have X. This is 1 now. So let's do that. All right, so I'm going to kind of erase all this. Okay, so let's do Y. We got to pick two other rows. Now, ideally, we'd pick two other rows where the concentration of H2 now is constant, but we don't have to now that we know the exponent of H2. So I'm going to pick rows 3 and 1, and I like to put the larger rate value on top just because that gives me a whole number that I can work with rather than, a fraction. So now I'm going to take rate 3, put that on top, and rate 1, put that on bottom, and say, hey, that's equal to K times the concentration of NO. In row 3, it's 0.2, and this is to the power of Y, times the concentration of H2, which is 0.1, to the power of 1 technically now, because we know that value, times K. In the denominator, it's going to be the row 1 values, so I have 0.10 to the power of Y times 0.10 to the power of 1. And again, these guys are going to cancel. They're the same value. And K is going to be the same because it's a constant. And so I can calculate all this out. Now, what this all simplifies to is 4 is equal to, again, we have 0.2 over 0.1 all to the power of Y, or in other words, 2 to the power of Y. So what does Y have to be in order for it to yield 4? Y is going to need to be 2. Okay, so now I can actually fill in my rate law. My rate law is going to be equal to K times the concentration of NO squared times the concentration of H2 to the power of 1 technically, but we generally don't draw the 1 or write the 1. Now I have one last bit of data I could calculate. I could calculate the rate constant, right? Now that I know the exponents, I can pick any one set of data here. I'm going to do 1 and solve for K. I know the rate is 1.23 times 10 to the negative 3, and that's equal to K times 0.10 squared times 0.10 to the power of 1. And so we can rearrange and solve for K. Now this is a third order reaction, so K does have units, and we're going to need to determine those as well. So the value I get is 1.23. Now, I need to think about units here. This is molarity squared, this is molarity to the power of 1, so total they get molarity cubed. This was molarity per second, so I need to divide molarity per second by molarity cubed, which if we think about this is going to be molarity to the negative 2 seconds, negative 2 seconds to the negative 1. This would be my rate constant and its units. All right, so let's continue for a little bit. Now, if you think about all of this, we need to talk about what if the ratios aren't simple, right? In the previous slide, we saw, hey, 2 is equal to 2 to the power of y, or x, sorry, and 4 is equal to 2 to the power of y. Just by inspection, I would expect everybody to be able to figure out what x and y are without having to do actually math. But what if it was like, something crazy, like I would think that this would be a much harder exponent to determine. I don't know about you. I can't just figure it out. So in this type of scenario, we need to use logs in order to solve for x, our exponent. Now, how do we do that? So let's look at that. So let's say we have a scenario where we have rate 1 and rate 2, like we were doing on the previous slide, and their rate law equations are like this. And we're going to divide them, rate 1 over rate 2. And for this case, let's say, hey, B's concentration is not changing, right? Like we did in the previous slide. And then we can go, great, hey, we can cancel it out and we get this. Now, if these two things are not easily determinable, right? They're not 2 and 4 or whatever, then what we can do is we can take the log of both sides of the equation. Now, when we take the log of this, we get some value. And if we take the log of this whole thing, we get this, log of the concentrations times m in the front. This brings the exponent out of the equation. Now the last step here would just be to divide over these two values. So let's go back to those numbers I had earlier, right? In this scenario, my rate here was 0.588 and this concentration factor was 0.126 to the power of m, right? That's what we were doing. Now if we take the log of both sides, we're going to get log of 1.588 is equal to log of that whole other thing, right? Log of this, and this turns into this, m times the log of 1.26. Now the way I can solve this is just divide over by this, right? Log of 1.26 gives me my m value. Now, if you actually do this division out, you're going to get like m is equal to almost exactly 2, which gives us our answer in a not easily distinguishable type of situation. So just thinking about this, there's one last thing we can do with that rate law. We learned on the 2 slides back that the rate law for that reaction was this, right? K is equal to 1.23. Yeah. And this exponent was 2, this exponent was 1. We can solve for the rate now at any concentration set that we want. So now we're, hey, given these two new concentrations and asked, hey, what's the initial rate at these different concentrations than what we had in the table? Well, now that I know the K value and the exponents in my rate law, I can solve for the rate of this reaction just by simply going, hey, here's my K value, here's the two new concentrations, plug them in, and we get a new initial rate for the system. And so from that table of data, we were able to find the rate law, meaning the equation's exponents, the rate constant, and the initial rate at a new given set of concentrations. All right, so that's the end of this lecture video. If you guys have any questions, as always, please come to discussion sessions or email me. I'm always available. Have a good day.